其实大家陆续回来，其实我就蛮好奇想知道你们多少人有买课本，或者有找到课本的？有找到课本的啊？因为现在时代比较不一样了，就是说以前的话，最早10年前我会就是甚至班代会帮忙购买课本的啊。但是因为有时候我们还是会去说请阅读课本，对不对？我在上课的时候请extended material，还是会告诉他请去找课本啊。所以我其实会比较好奇的是，但不用现在告诉我了啊。如果是这样告诉我，没有在课本的情况之下，怎么样准备考试还觉得充分吗？对，啊，就是你们现在的这种108课纲，对不对？自主学习啊，终身学习啊，适性扬才啊，共好还是什么？有些口号啊。Okay, we still have like 5 minutes. All right, so please take it easy. Now we'll resume the lecture 2:20 at 2:20 sharp. Yeah. 好，可以的哈，谢谢谢谢，好。Okay, so I think it's about time. let's move on to our next topic. Okay, please come back to DSP. Our next topic is FIR, finite impulse response. FIR filter design, and the method, there are actually two methods, okay? So the first method that we are going to talk about is the window method, okay? And literally you will see what is a window and how do we use it. We use it in the time domain. So the long story short, windowing is in time, okay? Windowing happens in time, and we'll see that when we window a signal in time, that corresponds to convolution in frequency. Okay, so I personally call this the convolution theorem of the second kind. Yeah, remember where else did we encounter convolution theorem? Anybody? Yeah, we have encountered convolution theorem, right? Convolution in time corresponds to multiplication in frequency, right? That's the first kind. Okay, but now it's kind of in the duality situation, in the dual situation, 对偶性的 dual. In a dual situation, this is duality. Fourier transform has a lot of duality properties. Okay, duality. Because of duality, then we expect that when we window means multiplication. Okay, so when we multiply two signals in the time domain, that corresponds to convolution of their frequency response in the frequency domain. Okay, so now we'll see that that's indeed the case, and then. For this lecture, we will also encounter, it turns out that window design of an FIR filter creates a phenomenon, an important, historically well-known phenomenon, which is called the Gibbs phenomenon, and which has some serious implication of the limitation about designing the filter using this method. It's a limitation, okay? So we'll talk about that. And then, but to work around, we'll also mention how to make a situation not so bad, how to compromise by choosing a window so that the bad property is reduced. Okay, we can suppress the ripple by wisely choosing a window, and there are different choices. Okay, choosing of the window function. So let's begin. Okay. So to begin, recall that. So please delete this. So in past years, it's not about homework number 2, problem 1. But let me first say it. Okay. So we know that an ideal filter. So the idea is that we want to approximate an ideal filter, and taking low pass as an example. So the beginning idea, the beginning point. Someone think about an ideal filter in the frequency domain. Okay, and now our frequency axis, there's no borrowing of analog prototype. We just start straight ahead in the discrete time domain. Okay, and now imagine that with small omega, imagine that we want an ideal filter, which has a cutoff frequency omega c, small omega, where c stands for cutoff. Okay, it stands for cutoff. Imagine we have a ideal filter with gain 1 in the passband and gain 0 in the stop band, with a cutoff frequency very sharp, immediate, rapid transition from 1 to 0. Okay, which is ideal. Okay, keeping every frequency in the passband, rejecting every frequency completely in the stop band, and this is the ideal behavior that we want. Okay, and very soon you realize that this cannot be implemented, and the reason why. The reason why is that if we do the inverse Fourier transform, okay? So allow me to denote this as G Ej omega, okay? If G is our ideal low-pass behavior in the frequency domain, so we can take the inverse DFT and obtain a closed form expression of the impulse response in the time domain. by applying, by definition, applying the inverse DTFT. Okay, so let's review what is the inverse DTFT. Inverse DTFT equals to 1 over 2 pi integral g what? E j omega n d, and we accumulate over all frequencies, right? So using this, you realize that the result is our good old friend. The result looks like a sinc function in the time domain, in the discrete time, okay? So I'll skip the derivation. The derivation should be pretty straightforward, okay? So we have seen very similar derivation in another context, but the result, end result is written right here. It's written right here for you. The end result, when we take the inverse DTFT, we get a very familiar expression. We get a very familiar expression of sinc function, some sort of sinc. And of course, you realize that at n equals to 0, this expression is not well defined. We have the situation with 0 divided by 0, right? So therefore, at n0, at time 0, not frequency, time, but time. At time 0, it should approach the value is this, okay? So let's just also copy. Maybe we don't need to copy it, okay? So the expression, do we need to copy it? Do you want to copy it? Okay, take it easy. Let me just copy it. Sine cutoff frequency n divided by pi n for any n, not 0 n. And at time 0, it goes to omega c divided by pi, where omega c is the cutoff frequency. Okay, so that's a result of applying inverse DTFT to obtain, this is our impulse response. Okay, this is our impulse response. And it's good to create a really wide sketch of the impulse response. Let's take a look, okay? Our ideal low-pass filter in the time domain should look like this sinc function in discrete time, okay? Let's say discrete 1, 2, 3, 4, 5, 6, 8, okay? -1, -2, 3, 4, 5, 6, 8, okay? Yeah. We're about to take a sketch, okay? I like sketching. I think sketching really helps us to clarify ideas. So let's take a sketch of what is the color frequency you want. Propose a color frequency. Anybody want to propose a color frequency? Anybody? Stephen, Ha? Propose a color frequency. What? Stephen, how about pi divided by 4? All right, so Stephen said omega color frequency pi divided by 4. Pi is Nyquist, right? So pi is Nyquist. So if pi is 2020 kilohertz, pi over 4 corresponds to 5,000 hertz. Yeah, just to clear our mind a bit. So let's say if pi, no, we do have a omega c. Then plug in number, okay? Easy enough, plug in number. Yeah. But wait, so now, for example, if omega is pi over 4, then what? Then we need to evaluate Gn equals to basically sine pi over 4n divided, seriously, that's what we mean, divided by pi n. Okay, yeah. Wow, nice. Okay. So it seems to me that when n equals to 2, and when n equals to multiple of 4, we get 0 crossing. Can we agree on that? 每隔4个点就有 cross 0一遍了。Is that clear? We get 0 crossing. So counting 1, 2, 3, 4. We got the first 0 crossing right here. Okay, so the impulse response in the time domain, and at time 0 it equals to omega c divided by pi. So that seems to be 1/4. Okay, 1/4 on top, and we have this envelope, and the impulse response should be what? Symmetric. So it should look like that. Yeah. the impulse response should look like that. Okay? And finally, to finish our sketch, just draw the stems that we need. Make stems, going negative, 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 zero crossing, positive, and so on and so forth. Okay? Thank you for the proposal. Okay? That's a result of designing an ideal low-pass filter with a color frequency of pi divided by 4. In the time domain, this is the result of taking the inverse Fourier transform, okay, to go from frequency back to time. Right? So far, so good? Yeah. But now immediately, this is G of n. Immediately, we see a problem. We have a serious problem. The problem is that this response goes to extend to indefinitely. 它这两边延伸到无穷啊。The response extends indefinitely on both sides of the time axis. Okay, extends to minus infinity, extends to plus infinity. The number, the impulse response never, it lasts forever. Okay, since ever and forever. Okay, yeah. And such kind of system, I tell you, cannot be implemented. Okay, cannot be implemented exactly because it's infinitely wide in time. Is that making sense? This cannot be implemented. 没办法实现的啊 It cannot not be implemented. So therefore, quickly, people came up with some naive idea. This is naive. Okay, 有点天真的 yeah. People came up with a naive idea of truncation. Truncation. So that is to say, all right, so let's keep all the samples between minus and plus n. Okay, so the idea that, all right, so to compromise, let's say this is minus n and plus n. Let's keep everything in this range. Okay? And then for anything outside this range, we are just going to give them up. Okay? Give them up. Sorry, you are not in the range. Sorry, sorry samples. We're going to neglect all of you. Go home and see you next time. All right. Just forget about anything else outside this range. Now this is a naive idea, okay? But turns out that we call this a design. This is design, an example of design using the window method. What is a window? Window, you can say that, oh, this is a range that we care, so that's a window, okay? By just keeping the middle part and ignore and omitting everything outside that range in time. Okay? So by doing that now, finally, this is something that can be implemented. Okay, that can be implemented, almost can be implemented. Why? Because now we have finitely many samples. Can we agree on that? Now we have only 2n plus 1 samples. So this is something that's manageable. Okay, we can implement this. You can just store every sample in an array, right? Of course, you can implement that. Store all the 2n plus 1 samples in an array, and then you're ready for implementation. Yeah, in terms of programming. Okay, just store everything. Store everything, okay? Store everything in a big array. Okay, store them in every sample right here, everything. Just store. My suggestion is just to store in a big array of a 2n plus 1. Okay, I don't know, float. Call it H, right? Yeah. This is just 大方一点 Call it H, to keep the name the same, right? Just create a room in your memory, and we are ready to store every sample in that array. You are ready for implementation. Okay, good news. Okay, naive, yeah, pretty naive. But it's a design. I claim to you that this is already not too bad. This design is not too bad. Okay? Really not too bad. Okay? But further, in the next slide, we are going to analyze what's going on. Okay? Now, by just keeping the middle part, just keeping the middle 2n plus 1 samples symmetrically on both sides, what kind of frequency effect will it create back in the frequency domain? Okay, because now ideal filter becomes not ideal anymore. Then what do we expect? Do we expect to see ripples? Do we expect to see a transition width? Yeah, what do we expect? Okay, so now in the next slide, we're going to see what will happen back in the frequency domain after we ask them, all of them outside range to go home. Okay, after we ask them and then to go home, what kind of effect will happen in the frequency domain? Okay, yeah, is that good? So far so good? We're going to take a look at frequency domain. But this is a design, okay? So as a result, consequently, when we need to know one thing, okay? Maybe we can come back to this slide later. I want to show the next slide, okay? The next slide is what will happen, shows us what will happen back in the frequency domain, okay? So now you take a look, we have another sync-like function. This is maybe potentially a confusing part, okay? This can cause some confusion, but now let me point out that this is theta is the frequency variable. And here we see that ideally, the ideal response, maybe let's look at it right here. The ideal response is G, okay? G, the ideal filter is, has a pass band and stop band, and we know that the Fourier transform repeats itself every 2 pi, right? That's a general property of DTFT, okay? So in this plot, we are seeing the pass band, stop band. Again, after pi, everything repeats, pass band, stop band, okay? So that's the ideal filter before windowing, before we truncate our impulse response. But now after truncation, the frequency response becomes like that in solid line, 实线, okay? Yeah. In the solid line, a solid thick line right here, that shows us the frequency response after truncation. After truncation, after that, okay? After only when you only keep 2n+1 samples, this is what happens, okay? The frequency response of your h of n. Now, h of n equals to gn if n is in between is in the middle, and 0 elsewhere. When we do that, then turns out that h of ej omega, this is the frequency response. This is the result of your design, okay? Your design becomes non-ideal. Okay? Your design becomes different from the ideal filter, of course, yeah. How different? First of all, there's a transition from passband to stop band. Okay, there's a finite transition. There's a transition width. Secondly, we have ripples both in the passband and in the stop band. Okay, so this is a very nice example of. Let me read the caption. This is a copy from the textbook. Okay, and now in this plot, D stands for desire. In the textbook, that's how, there's a discrepancy in the name. We call this G, okay? G is denoted by differently somehow, so be aware of that. But other than that, no transition width, it's too narrow. Other than that, and I also, oh, by the way, I have it by my notation, Hn. I might have denoted this as, to emphasize that we have a parameter to choose, okay? Did I denote our, let me take a look, yeah. Oh, yes, yeah. Yeah, so that's my notation. So I emphasize that now with a subscript big N, we can be aware that that indicates the length of our filter, okay? Yeah. So going back 2 slides later, about 2 slides, I want to show you the result first, okay? So here, the frequency response look like that, okay? Yeah. But in this figure, what it is trying to explain? This figure is trying to explain what we call the convergence theorem of the second kind. Okay? So so here we are actually seeing the convolution in the frequency domain. So the idea that you have two spectrums and we convolve it in the frequency domain. Okay? So the result is a convolution of a continuous spectrum, continuous but periodic spectrum. That's the ideal response. Now it's being convolved with another spectrum. And the result becomes that. Hopefully you can sort of create a mental picture of, yeah, indeed. If we convolve H with, actually it's, yeah, if we make a convolution, so it's a kind of a sketch showing you the end result. Let me emphasize that the end result right here is a convolution of two spectrums in the frequency domain. But how exactly? Okay? But how exactly? So I need to go back one slide. Okay? So please take a mental picture of what's going on. Okay? Take a mental picture. Now hide the picture, or take a mental picture in your brain, and we will go back one slide to explain the mathematics. Okay? We are going to explain the mathematics right here. The mathematics goes this way. The mathematics is that when we say H is the result, denotes the truncation. Okay? Truncation is, or equivalently, we can say that H of, in other words, H of n equals to G of n times a window function where W of n equals to 1 in that range and 0 elsewhere. Otherwise, 0 otherwise. Equivalently, we can think of truncation as this operation. They are equivalent. Keeping everything, don't change anything in the middle part, and making everything else 0, right? So that's equivalent to multiplying with this window function, right? These two things are equivalent. Just simply another way to say it. Can we agree on that? When we multiply with W, and W, what is W? W is all 1 in this range and all 0 outside that range. So therefore, we can rewrite Hn in as the product of G of n, which is our desired response, with the window function, with this window function, okay? So that's the entrance point. This is the entrance point because now the benefit, the advantage of this expression is that now we express H, our design, as the product, as multiplying two things in the time domain, right? So imagine that G of n is still our desired response, but now we multiply it with the window, what we call a window function. Or actually, this is called a rectangular window. Rectangular 矩形的长方形的 rectangular window. So now, if you understand that our design, the spirit of our design, the principle of our design is to do a multiplication in the time domain. So no wonder in the frequency domain we have convolution. Okay, we have convolution. Okay, so let me read the slide. Okay, so in the previous page, our design can be re-expressed as is our H equals to. Okay, I forgot our script. H, our design can be expressed in terms of the product of our ideal response times the window function, where W is 1 in that range and 0 elsewhere, for 0 elsewhere in that range. And this window is referred to as a rectangular window. Its length is 2n plus 1. Okay? And they multiply in time. Therefore, their frequency response, when we go back to the frequency domain, we have the convolution expression. Okay? So here the notation. Let me first introduce to you a notation. G being a spectrum, W being a spectrum. Okay? And here I'm being lazy a little bit. Okay, so note that here. Wait, yeah, I'm being sloppy. Okay, let me just explain to you. Just for simplicity, here we write omega instead of ej omega. Okay, we've been writing ej omega elsewhere, but here is really more convenient. If we agree that we are becoming sloppy in our notation, if big G is the Fourier transform of small g, big W is Fourier transform of small w, then let's agree on this notation for now. Can we? Can we agree on this more simple notation? 就是写方便了，写起来比较方便这样。And here is actually a theorem, okay? So the convolution theorem of the second kind goes that if we have multiplication in the time domain, then we have this circular convolution in the frequency domain. Okay? And circular convolution is defined by 1 over 2 pi. And here with an integral, but now it looks like they are convolving in the frequency domain by, let's say, flipping one of them and multiply and evaluate the integral. Okay? That's a convolution of two spectrums. Convolution of two spectrums. And we can have this notation, convolution with a circle. Sometimes I'll call it a circular convolution because the integral range is from minus pi to pi, making a circle. Okay, circular convolution of G and W defined like that. And this is a mathematical property that can be proven. That can be proven. Okay, so far so good. Yeah. Take a note of this definition of a circular convolution. We might need it somewhere. So maybe I can erase it. Okay, maybe I can erase this. And we know that it's cut off and Stephen's suggestions. Now let me erase something to make room for further discussion. All right. But now we have the convolution theorem of the second kind, and we know that the design would cause the frequency balance to be equal to now G omega circularly convolved with big W omega, and the definition goes 1 over 2 pi. Minus pi, 2 pi, G, and the dummy variable is theta, W, now omega minus theta, d theta, theta being the integral, the variable for integration. Okay, so with that, we have a few additional remarks. The first remark I've mentioned that here we have a sloppy notation. G theta is basically, big G is the Fourier transform of small g, making our notation easier. And secondly, note that in our definition right here, note that G of omega is our ideal response. It's all real valued, right? It's all real valued, being either 1 or 0. Real valued. Nice, okay? But how about W? Big W, it turns out that big W is also real valued. Both G and big W are real valued. And this will make our calculation easier. Okay? This will make things easier later. Okay, but let me mention it first. Both G, our ideal response, and it turns out that big W, if we define small w in the time domain like that, because of symmetry, it has an even symmetry in time. Therefore, the frequency response of small w is real valued. And these are some nice properties that will help us next, in our next step of derivation. It will help us later. Okay? So let me mention that. Is that good? That good? Both of them are real valued. Okay. And by the way, there are a few extra things that might need explanation. Yeah, a few extra points, extra items for discussion. or a few extra items for clarification. Let me put it this way. The first item for further clarification is that how do you prove this? Okay, proof of the convolution theorem of the second kind. Yeah. Okay, it's kind of it would be a nice exercise. Okay, with a nice exercise, I'm just showing you the result, mathematical result. But how do we prove it? Okay, how do you prove it? It's not too hard, but it remains to be clarified, right? If you haven't done so, if you haven't in your life proved the convolution theorem of the second kind, it's good to do it once in your life. Okay. So that's my attitude, right? Do it once in your life. Prove. But I'm just telling you, sharing with you as a matter of fact, right? But how do you prove it, right? So that's one item. Second item for clarification is that note that now this result of our design has nicely, finitely 2n plus 1 samples, right? But is this filter, this is an impulse response, right? But is this impulse response, is it causal? Is it causal according to the definition of causality? Take a look. Second item, causal, Hn of n is not causal. Right? So I'm kind of like slapping my own face, right? Because I mentioned earlier that in this semester we all deal with causal filters, right? But now we have an example. At least in the middle of our derivation, I suggest that let's think about a filter which is non-causal. Okay, so please bear with me. Okay, but I want to point it to you. H is non-causal. Okay, so mathematically it's non-causal, but in practice. Let me mention that in practice, after making it finite length, in practice, our final design should be shifted in time, okay? Making it causal. So our final design, if I denote our final design of impulse response should be Hn of n shifted to the which direction? Shifted to the right. Shifted to the right, but simply shifting to the right by n sample, we have made it causal, okay? So no big deal. This is non-causal, it's not a big deal. So later, just keep in mind, in reality, when you store every filter coefficient in an array, just implicitly, 其实很不明确隐含的，对不对？ Implicitly 隐含着 what's going on? 隐含着 you are shifting every sample to the right by n, making it causal. So in the end of our implementation, when you use your filter by applying those coefficients in that array, shift it to the right by n samples, and we can implement it. Okay, so causality is not a big issue. It's uncomfortable to a certain extent, but it's not a big issue. Okay, so I want to point this out first. Okay, Hn mathematically is non-causal, but it's okay. In practice, we will always shift it to the right and make it causal, make everything perfectly causal. That making sense? Or in practice, after shifting to the right, so now your output, now you have a filter, we claim. Now your output is x of n convolve in time with h, your FIR filter. So now in practice, this is what we do. In practice, you know that convolution can be implemented as long as the filter is causal. Okay, so in the end, it's not a problem. This is the way we are going to use our filter. Okay. Okay. So with these extra remarks, now we are. Do you want to mathematically derive this, or do you want to see the next page first? Probably no mathematical derivation. It's not too hard. Okay, maybe it will be a follow-up. but yeah. So, but with this in mind, convolution in frequency. Yeah, we've copied the notation, right? The definition right here. So let's see what's going on according to this definition. What will happen when we convolve the ideal response with the Fourier transform of W. So now, on this page, you are looking at the Fourier transform of W. And this is super confusing. I claim to you, this is very confusing. Unfortunately, the Fourier transform of W turns out to be also to look like sinc. So you see, this is quite confusing. We have sinc in time, sometimes we have sinc function in time, sometimes we have sinc-looking function in frequency. But unfortunately, okay, I admit. Turns out that W, if you look at the Fourier transform of W, it looks like a sinc function. But please, let's refrain from calling it sinc, okay? But instead, I have a suggestion, okay? Instead, just by observation, if W is a rectangular window, and it turns out that I want you to take home, okay? I want you to now remember that generally speaking, and this will show up again and again, generally speaking, the Fourier transform of a window function usually has a main lobe and a few side lobes. That's all you need to remember. Okay? The Fourier transform of your window function generally has a middle part we call main lobe, and some other things, ripples if you will, called side lobes. Okay? So maybe it's good to do some sketch again. Yeah, sketch time. Yeah. If W is something in time, so in our case, 1 in the range, and 0 otherwise, and we'll see a few other windows. Okay, this is our rectangular window. Okay, and in general, when this goes to the frequency domain, when we evaluate the spectrum, its spectrum as a function of small omega. Generally, we have a main lobe with 0 crossing. And this is called the main lobe. Main lobe. Okay. In addition, we have side lobes. Okay, and all the drawing will end on at frequency pi. Okay. All these nice little other things are called side lobes. So these are some terminologies for us to cover. Okay, main lobe versus side lobes. Main lobe, side lobe. Main lobe being the middle part. Okay, so as an example, if the Fourier transform now. Can you imagine the convolution their convolution in frequency? That's our next activity. Okay? With the Fourier transform of the window function, now if you make it a convolution with the ideal low-pass response, does it make sense? Yeah, it makes sense. Convolution of a square-looking periodic function with another function which is narrow but having a main lobe and some ripples we call side lobes. When we make the convolution, what does it mean to make a convolution? Convolution means to calculate sort of overlap area, right? So anyway, the result looks like that. Okay, the result looks like that, and the result looks like that. The result is not ideal anymore. The result is not ideal anymore. So that's kind of the FIR design, the first example. Now we have the first example of designing an FIR low-pass filter. Okay? So sort of to recap, we have an ideal filter to begin with, no analog prototype. Okay, we have ideal filter to begin with, and we know that it's rather easy to derive its impulse response back in time, and by just keeping the middle 2 n+1 samples, then we know that this will happen in the frequency domain, and this is the end. This is the performance, if you will. This shows the performance. Okay? the performance of approximating an low-pass ideal filter in the frequency domain, there is going to be some error. Okay, there's going to be some error. The pass band is not a constant anymore. The stop band is not zero all everywhere. It's not ideal, but it's not too bad, right? Still, you can kind of recognize there is the pass band and there's a stop band. Okay, still you can kind of recognize. Yeah, not a bad idea. Really, this is not a bad idea. It has been used everywhere. Yeah. So in the end of this slide, I have a discussion item that we may cover next week. Okay. So in the next week when we come back, let's have a discussion. Let's have a discussion that we want to predict the performance when we increase n. Right? How long is n enough? Okay, if you want to design, as Stephen suggested, a filter with color frequency. Thank you, Stephen, for the proposal. Nicely chosen, a nice example. We want to design a low-pass filter with a color at pi/4. How large of n should we pursue? Is n equals to 200 enough? Is n equal to 500 enough? Or n merely needs to equal to 32 or 8 or something? 8 is probably not enough. 8 is like truncating right here. Probably not a good idea. But how long should it last? So again, this is a trade-off. The performance got to improve, right? Because by including more and more samples, the performance got to improve. But in what way? In what sense? That's what we will discuss when we come back next week. Okay? And what time do we have? And all the discussion will go back to our spec. Okay? Will our transition width become narrower? Will our ripples become smaller when we increase n? Generally, that's the direction that we need to discuss when we come back next week. Okay? And and I will have an exercise. I will work on plotting the frequency response as we increase n. Okay? That will be an exercise for next week. We are going to plot similarly when we increase n. This is an example of n equals to whatever, yeah, on the textbook. Okay, but how about if we double n? If we increase n by 2 times, what do we expect? Do we expect a sharper transition? Do we expect a smaller ripples? Will the result converges to ideal when n approaches infinity? Of course, yes. Yeah. But in what sense? Okay. So these are some very nice properties that we will discover next week. Okay. Yeah. So I'm going kind of fast today. 好吧，今天有点，希望大家不要觉得我很混啊。Yeah. And I hate to ask any questions. Yeah, usually there's no question. And I don't have a story to tell. Like last time, I tell you that I had an interview with Qualcomm, right? Yeah, last Thursday. I don't have a nice story like that. Okay, so I'll stay in the classroom for a few more minutes. So that's it all I want to share for now. I think it's nice to go home with a few questions. Okay, go home with a few questions. When we come back, we are ready for discussion, right? Thank you for being here. That's it for today.
就是从哪里知道说，就是这个 W